Welcome to the course on biostatistics and design of experiments. We will continue on the topic of ANOVA. Let us look at one more problem. So, look at this problem. This has got 3 different parameters, or we call it independent variables, or we will call it groups. Imagine I am doing a bioprocess experiment. Okay, this is a 3-way ANOVA. Okay, I want to maximize the production of a metabolite. The 3 main effects are carbon, nitrogen and organism. Okay, so how do I go about doing it? There are so many ways. Suppose I change one parameter at a time, and then I may get about maybe 21 experiments, 7, 7, 7 like that, but then that is not a very good approach. If you want to look at interactions, we may have to change many parameters at a time, correct? So there are many approaches. One is called the factorial design, then another one is called the fractional factorial design, then there are some second order designs and so on. But one of the designs is called the Latin square design. Okay, look at this design. What is happening is I am putting these 7 carbon sources as heading for the column and 7 organisms here, okay, and then we are changing nitrogen in certain fashion. So, N1, N2, N3, N4, N5, N6, N7, and then you have different nitrogen for these oxygens and carbons. So, but the total number of N1s will come out to be 1 in this column, and total number of N2 will come out, okay, to be 1, N3 will come out to be 1, and so on actually. So, that way there is some sort of a symmetry. So, if you take this particular experiment, I will be doing with the carbon 1, it is called level 1, or it could be called carbon with that particular concentration, then nitrogen at a particular concentration, and with the organism 1. Okay. Now, if suppose I take this particular experiment, I am doing carbon at a particular level of 7, nitrogen at a particular level of 4 with organism 7. Okay. So, these are the total number of experiments. So, what I am doing is I am doing totally 49 experiments, right. Okay. I am doing totally 49 experiments, and these are the results given here. We are looking at a metabolite which we want to maximize. Okay, it could be in quantity of milligrams per liter here. Okay, so we have it here 98. So, when I use a certain amount of carbon level 1, nitrogen level 1 with organism 1, I get 98 milligrams per liter of my product. So, suppose if I take this, I am taking carbon at level 7, nitrogen at level 4 with organism 7, I get 187 milligrams per liter. So, now I want to look at the main effects. What is the effect of carbon, what is the effect of nitrogen, what is the effect of organism, and so on here. So, we are doing 49 experiments. So, if you remember, long time back I introduced the concept of Latin square. Okay. So, we were doing a Latin square design, it is called a 4×4 Latin square. So, we were looking at 4 varieties of rice A, B, C, D, and 4 different fertilization strategies. Okay. So, what do I do is I take variety A, B, C, D, I give a treatment 1, day 1, day 2, day 3, day 4 consecutively. So, the treatment 1 is given to rice variety A on day 1, on day 2 treatment 1 is given to rice variety B, and on day 3 you give the treatment 1 to rice variety C, and on day 4 you give the treatment 1 to rice variety D. So, on day 1 A will be getting treatment 1, B will be getting treatment 2, C will be getting treatment 3, and D will be getting treatment 4. So, this is a 4×4, and because you have 4 different varieties of rice and 4 different treatment strategies, we have totally 16 blocks here. You can see this A, B, C, D, and the beauty is it is very symmetrical. So, if you add, if you look at it, A will appear only once, okay, B will appear only once. Similarly, if you go this way, A will appear only once, B will appear only once, C will appear only once. So, here you are doing 16 experiments. Okay. Now, in our problem it is not really completely symmetric with respect to A, B, C, because oxygen the organism you are trying it out, okay, all the organisms carbons are being tried out. So, organism versus carbon is being tried out, okay, in different combinations. Okay. For example, organism 2 is being tried out on with carbon amount 1, carbon amount 2, carbon amount 3 and so on, but if you look at the nitrogen amount, it is not exactly as much. So, ideally if you want to do a complete factorial, it will be like a cubical 7 into 7 into 7 type of, that is a huge number. 7 into 7 is 49, and then when you are multiplying again by 7, that is going to be a big number, right. So, that sort of approach we are not going to do, whereas we are doing much less number of experiments. That means we are doing only 49 experiments here in this particular case, and although the organism and the carbon amounts are being done in a full factorial, that means all the values, nitrogen is not completely being looked at. For example, if you take nitrogen 1, you look at nitrogen 1 is being tried out only with the organism 1 at a carbon level 1, but it is not tried out at all carbon levels, but still it is very useful because you are going to do less number of experiments, but you will get a lot of information on the main effects. Okay, let us go back to the problem, and so this is called a Latin square design. We are looking at a carbon at 7 different levels or 7 different sources of carbon, nitrogen maybe at 7 different sources of nitrogen like ammonium based, inorganic or organic, different types of nitrates, sulfates, phosphates and so on. Carbon could be yeast media or LB media and so on, organisms, different types of organisms here. Okay, so if we take 49 experiments, let us go back to ANOVA and see how to work at it. So, as you know how to do the sum of squares with respect to the carbon, sum of squares with respect to the nitrogen, sum of squares with respect to the organism, total sum of squares. You subtract each one of the individual group sum of squares from total sum of squares, that will give you an error sum of squares. Okay. So, that is the general approach by which one goes about handling this problem. Okay, let us look at the problem. So, again go back to the problem here. So, if you look at the row, you will get an average. This is the average for organism 1, this is the average for organism 2. That means I am adding up all these terms and dividing by 7, and this is for the organism 3. I am adding up all these dividing by 7, adding up all these dividing by 7. Okay, we got the hang of it. Now, for carbon I have to just add up the columns and divide by 7. So, this is the average for carbon 1, this is the average for carbon 2, this is the average for carbon 3, 4, 5 and 6, okay, and 7. Now, understand, average for carbon, average for nitrogen. Now, we can get a grand average. Okay. What is grand average? Average of all these averages. Okay. So, it could from the organism, if I add up all and then divide by 7 I should get, or from carbon if I add up all these and divide by 7 I should be able to get that. So, straightforward, this is the grand average. So, we have 7 values for average organism along the rows, 7 for carbon along the columns. Okay, now we need to get sum of squares for we will look at nitrogen in the next slide, but we need to get the sum of squares for carbon, sum of squares for the organism. So, it is very straightforward. So, what do? We multiply by 7 here because there are 7 items here. We take the grand average 93.61 minus 71.71 square. Okay. 7 into, because there are 7 items, 93.61 minus 71.7 square. Okay. So, next item 7 into 76.85 minus 93.6 square. This item 7 into 76.1 minus 93.6 square and so on. This item 7 into 86 minus 93.6 square. Okay. Okay. And okay, this item 93 minus 203 square 7. Okay. So, we add up all these things, that will give you the sum of squares for carbon. Do you understand? So, we have the averages for carbon, we subtract each one of the item with the grand average, square it up, every time we have to multiply by 7 because there are 7 terms here. Now for the organism what do? We again multiply by 7 because there are 7 items here. 115.28 minus grand average 93.61 square, 7 into 95 minus 93.2 square, 7 into 84.4 minus 93.6 square, 7 into 77.4 minus 93.6 square, 7 into 101 minus 93.6 square. Okay. Finally 7 into 88.1 minus 93.6 square. So if you add up all these, we will get the organism sum of squares. So you know how to do the carbon sum of squares and now the organism sum of squares. Now let us look at the nitrogen sum of squares. So it is very straightforward. So we need to first get the average, 7 different averages for nitrogen. So nitrogen 1, how do we do that? Nitrogen 1 is here, 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 nitrogen 1 is here. So you add up all these items. So it is not in a column or in a row, it is in different places. Okay? It is in a different places, understood. So we add up all these, divide by 7, that will give you nitrogen 1. Then nitrogen 2 here, 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 add up all these, divide by 7. Okay, nitrogen 3, so we have here, 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 we have here and we have here, divide by 7, nitrogen 3. So like that we can do for all the nitrogen. So we will get 7 different nitrogen averages. So nitrogen averages are a little bit tricky because the organism average is along the row, carbon average is along the column, but nitrogens are spread all over the place. You can see N1, 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 N1. So you have to pick up all these randomly put. It is not very random because it is beautifully arranged, so that as you can see in each row you will have only 1 nitrogen. Okay. So it will not be 2 nitrogens, only 1 will come here. So it is very beautifully done, that is why it is called a Latin square design. We will look at these type of designs later on when we look at design of experiments. Okay. So we pick up like that and then add it up, sum it up and then divide by 7. That is how you do that for each of these nitrogen. So nitrogen is a little bit tricky. Now how do you take the sum of squares for nitrogen? So we know the average, okay, this is the average 84.8 and then you know the grand average, okay, you know the grand average. So what do you do? So you know the average, you know the grand average. So each one of them you subtract, square it up, multiply by 7. So you should get this particular row for nitrogen. Okay. So each of the averages are like this, 84.8. This column gives you the sum of nitrogens. Okay. Then divide by 7 you get this. Okay. So 84. So how do you do? 84.85 or 86 minus 93.6 multiplied by 7. 95.2 minus 93.6 square multiplied by 7. 98.1 minus 93.6 square multiplied by 7, like that you do and then you add up, you will get the sum of squares for nitrogen. So these are the main parameters or main groups or main independent variables, different names I am giving. So you did experiment by varying a carbon source or carbon concentration, you did experiments by varying nitrogen source or nitrogen concentration, you did experiments by varying organisms, 7 types of organisms, 7 levels of carbons or 7 different carbon sources, 7 levels of nitrogen or 7 different types of nitrogen source. So we got sum of squares for carbon, sum of squares for organism, sum of squares for nitrogen, because these are the 3 main effects. So look at the different terminologies by which I am addressing this. We can call it main effects, we can call it groups, we can call it independent variables. Okay. So we have 3 independent variables, carbon, nitrogen and organism, or main effects are carbon, nitrogen and organism, principal effects carbon, nitrogen, organism. Okay. These are the 3 independent variables in our problem. So different names are there. So what is the dependent variable? Your yield, okay, the yield of your metabolite. Okay, so we calculated the sum of squares for carbon, sum of squares for organisms, sum of squares for nitrogen. Now the question is, how do you calculate total sum of squares? So it is very simple. Okay, total sum of squares, we all know how to do that, right? We have the grand average, so each item we subtract, square it up, so you will get 49 different terms. Add up all of them, that will give you total sum of squares. Do you understand? Okay, so each one of these items we subtract, square it up, so that is the variation with respect to the grand average. Okay, now how do you calculate the error sum of squares? So we have the principal effects or the main effects, 3 main effects: carbon, organism, nitrogen. We have the total sum of squares, so we subtract each one of them and we get something called error sum of squares. Okay, that is called the error sum of squares. Now we will go to the ANOVA table. Okay, so we go to the ANOVA table, prepare your ANOVA table. Sum of squares for carbon 99103, 99103, sum of squares for organism 6317.9, sum of squares for nitrogen 5495.6, total sum of squares is 124451. So how do you get the error sum of squares? We subtract each one of these from this. This is an indication of the error. Now there are totally 7 into 7, 49 data points. Okay, as you can see, remember this, right? Our table 7 into 7, so it is a 49 data points. So we do degrees of freedom for total sum of squares is 48. We have 7 different carbon sources or carbon concentrations, so degrees of freedom is 6. We have 7 different organisms, so degrees of freedom is 6. So 7 different nitrogen, so we have degrees of freedom is 6. So error sum of squares 18, 6 plus 6 plus 6, 48 minus 18 gives you 30. That is the error sum of squares. Okay. So how do you get the mean sum of squares? You divide this divided by 6, this divided by 6, this divided by 6, this divided by 30. So mean sum of squares. How do you do the F table? F ratio, this divided by this gives you 36, this divided by this gives you 2.3, this divided by this gives you. So these are the F values. Now we need to compare with the F table for 6 into 30 degrees of freedom for a probability of 0.05. Okay, for a probability of 0.05. Okay, so let us go to the table. 6 and 30 degrees of freedom. So 6 we have 30, we go down 2.42. So 2.42 is your F table value, your F calculated value is 36.6, 2.33, 2.03. So this is larger than the table value, so we can reject the null hypothesis. So we can say that the carbon have a significant effect on the yield. Okay. So we reject the null hypothesis, so we say carbon has a significant effect on the yield. Okay, so we look at the average of these carbons. Look at this, 71, 76, 76, 67, 74. So this carbon 7, this looks very big. So this particular carbon gives you the maximum yield of your metabolite. Okay. Now let us look at the other terms. Organism 2.33, 2.42. So although we will say that it does not have an effect, that means organism, there is no reason for you to reject the null hypothesis, but still it is pretty close, you understand. 2.33 and 2.442 is not very far. So I may look at it more in detail, maybe carry out more experiments and so on. So although first hand we can say organism does not have an effect because there is no reason for you to reject the null hypothesis, but still it is not very far. So you better watch out, maybe do more experiments to get more data. So let us go back to the organisms. So this gives you 115, 95, 84, 77, 101, 94. So although statistically the table value is higher than the calculated value. So, there is, we do not reject the null hypothesis, this organism gives you the best so far in this list. So, we may do more experiments to be sure that organisms whether they play or do not play an effect. Okay, now let us go to the nitrogen. Okay, nitrogen is 2.03, 2.42. So, we can say nitrogen does not play a role, but again they are not very far away. So, we may go and look into the nitrogen. Okay, nitrogen, these are the various nitrogen, look at these averages. This nitrogen 6 seem to be giving a larger number when compared to these numbers. So, one may try to do more experiments with nitrogen 6 to be sure whether it is prudent to accept the null hypothesis or reject the null hypothesis. Do you understand? So, on first hand we can say only the carbon has an effect because the table value is less than the calculated value. So, only carbon has a significant role, that means we reject the null hypothesis and we accept the alternate hypothesis. Organism does not seem to play a role because F calculated is less than the table value. So, but then as I am saying then differences are not very large. So, one may try to do more experiments to be sure about it, and on just by a casual look this organism is giving the highest number of the metabolite. So, one may do more experiments to be sure about it, and the same thing with nitrogen, either you can say nitrogen does not play a role or 2.03 and 2.42 are not very far. So, do I again look at the nitrogen data and say this looks like a good giving maximum. So, maybe I do more experiments to be sure whether categorically I will accept the null hypothesis or reject the null hypothesis. But if you go very strictly by the statistical rules, we reject the null hypothesis only for the carbon, whereas we accept the null hypothesis for the organism and nitrogen. Okay. Now, another interesting point we need to consider is can I look at interactions? The problem is we will not be able to look at interactions. Okay. Why? I mentioned it long time back. So, if I want to look at, say for example, carbon oxygen organism interaction and I have 6 degrees 6 degrees. So, carbon organism will become 36 degrees of freedom, but I have only 30 for error. So, I will not be able to look at interaction. That means my number of experiments are not sufficient. Suppose if I had repeated the experiments if I had replicated the experiments, not repeated, please note we should not use the word repeat, although we in English we use casually repeat. We replicate the experiments twice, that means each of the experiments we from the beginning we completely do it with these combinations 2 times, this combinations 2 times. So, you will end up having 49 into 2 experiments. So, your degrees of freedom will be 98. Then for interaction of carbon organism 36. So, even if you subtract you will get some error degree of freedom. But as of now, because you have not replicated the experiments, if I cannot look at say carbon organism interactions because that will require 36 degrees of freedom. I have only 30 degrees of freedom, remember that. Okay. In previous one class also I did talk about if you do not replicate you will not look at interactions. Okay. In same thing here also, if you are not replicating you will not be able to really see if you want to see say interaction of one of these variables, because each of the interactions will require 36 degrees of freedom. So, we can just combine together and we will call it only the error. Okay, we will call it the error sum of squares in this particular case, and we can get a good F value for the carbon, for the organism, for the nitrogen. But if you want to really look at interactions, then obviously we may have to do replications and so on actually. Okay, so you understand this problem, it is very interesting problem, it is a 3 by 3 ANOVA problem. Okay, and it is called a Latin square design. We are varying 3 variables. One is the carbon source, another is the nitrogen source, another is the organism. So, although there are 7, 7, 7, we are not doing 7 into 7 into 7 experiments, we are doing only 49 experiments. So, organisms and carbon completely is done in detail, whereas the nitrogen is done only once. Okay. For each row we have only one nitrogen. Okay. Otherwise, if you want to do a complete factorial design, it will be like 7 into 7 into 7, like a cubic, right, whereas here it is like a square. Okay. And that is why it is called Latin square design, and nitrogen for example appears only once in each of these row, that way it is very symmetric. Okay. So, I do the experiments, these are the results. Okay. The carbon, nitrogen and organism is called the principal effect or main effect. Okay. We looked at how to calculate the average for carbon, which is easy along the column, average for organism along the row. Once we have the global average, we subtract each one of the average, square it up, multiply by 7, because there are 7 items, we get the sum of squares for carbon and organism. Okay, carbon and organism. But for nitrogen it is a little bit tricky, because nitrogen 1 is coming here, 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 here and here. So, we need to take an average of these 7 items which are spread in different places. For nitrogen 2 also we do the same thing, we have to take average of this, 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 this and this, like that. Okay. Then again we can take the sum of squares for nitrogen the same way for the other two, from by subtracting it from the global average, square it up and multiply by 7. And then total sum of squares is from each of the grand average or global average, you subtract each of these item and square it up. So, if you go to our ANOVA table, you have the sum of squares for carbon, sum of squares for the organism, sum of squares for the nitrogen, and then you have the total sum of squares, then subtract each one of these main effects from the total, you get the error sum of squares. Degrees of freedom 49 experiments, so you have 48 degrees of freedom, you subtract each one of these 6 minus 6 minus 6, you get 30. Why 6? We have 7 carbon sources, 7 nitrogen sources and 7 nitrogen organisms. Then mean, you know how to do this divided by this, this divided by this, this divided by this, this divided by 30. Now, the F value you each of these divided by error sum of squares. Okay. So, F table for 6 and 30 degrees of freedom comes out to be 2.42. So, it is very clearly showing that carbon we can reject the null hypothesis, accept the alternate. So, there is a variation in the carbon sources, but we cannot reject the organism and nitrogen. But then on second thought, if you look at this number 2.33 and 2.42, we can say they are very close. So, obviously I need to do more experiments to be 100% sure whether I completely accept the null hypothesis or not. And same thing here also, 2.03 and 2.42 is not very far away. So, do I do more experiments on the nitrogen to be very sure to accept or reject the null hypothesis. So, we looked at a very interesting 7 by 7 Latin square design. It is a 3-way ANOVA, but we are not able to see interactions because we did not do any replicates. So, the number of degrees of freedom is also very less if you want to bring in the interaction effects also. Okay, we will continue with the ANOVA in the next class also. Thank you very much.